Hello my dear students. So I'm going to continue with the extra questions related to hydrostatic pressure. Extra question 11. In that first one, depth of a water body is 1.8 meters. Calculate the pressure exerted by water at that point. Density of water is given to you 1000 kg per meter cube and gravitational acceleration 10 meters per second square. So you're familiar with this type of question. We use the same equation. Pressure equals height into density into gravitational acceleration. So I will directly use the equation P equals H rho G. What is H here? 1.8 meters. Rho is density 1000 kilogram meter minus 3. And gravitational acceleration 10 meters per second square. So if you calculate the pressure, it will be equal to 18,000 Pascal. 1.8 into 1000 into 10. So it's going to be 18,000 Pascal. That is a direct substitution of the equation and the calculation. So I'm sure you can do this by yourself. Then the second one. Calculate the force exerted by water in the above water body over a surface area of 400 centimeters square. We have discussed similar questions like this. So here you need to find the force. So how do we do that? If we are to relate pressure to force, what is the equation? Pressure equals force or perpendicular force divided by surface area. We can simply write it as force over area. So if you need to find force, you need to multiply pressure by area. That is by rearranging the equation. So we already know the pressure exerted by water 18,000 Pascal. And here you need to use area. Area is 400 centimeters square. Now if it is 400 centimeters square, what do we need to do? We need to have the standard unit. So to get the standard unit, what do? We need to divide it by 100 into 100. So that centimeter square will be converted to meter square. So 400 should be divided by 100 into 100 or 10,000. Then you will get the answer in meter square. So then if we simplify and get the answer, here of course I can, okay. So you get it as 180 into 4 Pascal into meters. It will be in newtons. So the answer will be 720 newtons. So 720 Newton is the force exerted over an area of 400 centimeters square. So to relate pressure with force, we need to use this equation. Pressure equals force over area. You rearrange it. So force will be equal to pressure into area. So when you substitute, you need to confirm or you need to look at the units carefully. Pressure has to be in Pascal or Newton meter minus 2 and the area has to be in meter square. Otherwise, you need to convert like this. So we have converted it to meter square. So you get the answer as 720 Newton. With that, students, we will move on to the next question. Extra question 12. Solids, liquids and gases exert pressure. Gases exert pressure in two ways. What are they? What are the ways in which gases exert pressure? One way, they exert pressure due to their weight. Like the solids as well as liquids, the height of the liquid column that exerts the pressure. Similar to that, gases also exert pressure due to their weight. Weight is the force. So force over unit area will give rise to the pressure. The second method is when you compress a gas. Compression means by applying the force, you decrease the volume of the gas. So there, a compressed gas always tries to expand. And when it expands, it exerts a pressure. That is the second method by which gases exert pressure. So here if we write the answer, gases exert pressure in two ways. What are they? Due to their weight, that is one. Second one, when a compressed gas tries to expand, it exerts pressure. So, two methods by which gases exert pressure. Due to their weight and when the compressed gas tries to expand, it exerts pressure. Then the next one. What is the standard unit of pressure exerted by gases? What is the standard unit? Whether it's solids, liquids or gases, it is irrelevant. The standard unit of pressure is pascals. So, what is the standard unit of pressure exerted by gases? Pascal. You can write it this way or you can write the unit itself, Pascal. Is it a vector quantity or scalar quantity? You know that. It is a scalar quantity. Why? Because pressure does not have a direction. It only has a magnitude. Or in other words, you can think gases, liquids, they exert pressure in all directions. So that means they don't have a direction. So they are scalar quantity. It is a scalar quantity. Scalar quantity. So gases exert pressure in two ways. Then the standard unit of pressure is Pascal and it is a scalar quantity. So I am sure students you would have answered these questions correctly. With that, I will move on to the next question. Extra question 13. Diagram of a cylindrical container filled with mercury is given below. So here the diagram is given to you. This is a cylindrical container. So there is mercury inside. Here you can see the height is marked as h. The height of the mercury column. So height of the mercury column is h. Density of mercury is rho. And gravitational acceleration is g. And the bottom surface area of the container is A. So here this bottom surface area is A and also they have given the gravitational acceleration g, density rho. So those are the values given to us. Write an expression for the pressure exerted by the mercury column on the bottom surface of the container. So although they have given us the area, when we consider the pressure exerted by a liquid column, we don't have to consider the area. You all know the relationship. You know the equation for pressure. Pressure is equal to height of the liquid column into density into gravitational acceleration. So there, if we are to write the expression, we will say P is pressure. They haven't given any symbol for pressure. So we will say pressure. You can either write pressure equals P and write the expression, or directly we can write it as pressure equals to H into rho into G. Or in other words, P equals H rho G. That is the expression. The second one. The density of mercury is 13,600 kg per meter cube. And gravitational acceleration is equal to 10 meters per second square. Determine the pressure exerted by the mercury column of height 0.2 meters. So, using this expression or equation, we can calculate the pressure. Pressure is equal to 0.2, or I will rewrite the equation. It's always better to write the equation and substitute. Pressure equals H rho G. So, H is equal to 0.2 meters and density 13,600 into gravitational acceleration 10 meter per second square. So here if we write it, it will be, you can simplify these two. So 2 into 13,600. 27,200 Pascal. Or if you want, you can write it as 2.72 into 10 to the power of 4 Pascal. Either way is fine. 27,200 Pascal. That is the answer. Because height is 0.2 meters, density is 13,600 and gravitational acceleration 10. So when you simplify, you get the answer as 27,200 Pascal. So I am sure students, you were able to do this calculation on your own correctly. The next one, extra question 14. You are provided with a 1 meter long glass tube with one end sealed, required amount of mercury and a glass vessel. Draw a diagram of the barometer used to measure the atmospheric pressure. So this is the Mercury Barometer. When they say draw the diagram, you need to label the parts as well. So if we draw the diagram there, you need to have the glass tube, so one end of the glass tube is sealed. Then here we will have the mercury there, and there will be mercury inside as well. So this part is going to be mercury, and here also we will have mercury. So what are these? Glass tube. I will put the glass tube here. Glass tube. This is mercury, and also they have said glass vessel. Glass vessel. What is in here? How do we do this? We need to fill mercury up to the brim of the glass tube so that there are no gas bubbles inside it, and then you invert it, insert it into the mercury here, that is there inside the glass vessel, and then when you stand it or when you attach it to a stand, or you can even keep it right to the bottom, that doesn't matter. It doesn't matter whether the glass tube is touching the bottom or it's slightly up, but it has to be below this mercury level. That is the important thing. So when you draw, also make sure that this part, the end of the glass tube, is below the mercury level. That is important. And here there will be vacuum. There will be vacuum. Nothing should be there. That's very, very important. Then only you will get the correct reading for the atmospheric pressure. How do we read the atmospheric pressure? We take the height of this mercury column, and the height has to be from this point to this point only. Not here. It has to be up to that point. What is the reason? Because there is atmospheric pressure acting here. There is pressure exerted by the mercury column. Pressure at this point and this point are equal. So then the pressure exerted by the mercury column will be equal to the atmospheric pressure. So this is the diagram of the barometer used to measure the atmospheric pressure. What do we call this? A mercury barometer. A mercury barometer. So that is the one we have drawn here. So this is what you were supposed to do there. I am sure students, even you all are able to vacuum. So that has to be vacuum, glass tube, then mercury, glass vessel, mercury barometer. So that is how you are supposed to draw the diagram, and I am sure you would have done it correctly. With that, I will move on to the next question. Extra question 50. What will be the height of the mercury column if the mercury barometer is kept in the laboratory? So, normally laboratory, if we take it, it is usually considered as the mean sea level. So, if it is mean sea level, what will be the height? It will be 76 centimeter mercury. Unless if it is a place where we have the lab at a very high elevation, the atmospheric pressure will be equal to 76 centimeter mercury. So, here we will say 76 centimeter mercury. So, since they have not given us where the lab is, if you want, just to confirm your answer, you can also say if it is at mean sea level. So, but here, what will be the height of the mercury column if the mercury barometer is kept in the laboratory, right? So, if we write it as 76 centimeter mercury, that is correct. Second one, what will be the height of the column if water was used instead of mercury? We have done this calculation before also. So, earlier when we did the calculation, we calculated the pressure exerted by the mercury column. Then we calculated the height of the water column. So, here what I will do is, I will do it in a slightly different method. So, atmospheric pressure is equal to pressure exerted by mercury column. I will write it as pH Hg, that is equal to pressure exerted by water column. That is, we will take it as pH2O. Both are equal. So, since pHg is equal to P water, and that is actually given by H rho G. So, here students, if we are to do the calculation, we can directly write the values for pressure exerted by mercury column. We know the height of the mercury column 76, but what do we need to do? We need to convert it to meters. So, 76 divided by 100 meters and density of mercury. Usually, it will be given to you in your paper 13,600 kilogram meter minus 3. But after doing so many calculations, I am sure students, you all remember all these values by heart. So, then we need to have gravity, but I will use G because in both sides, on both sides for pressure exerted by mercury and pressure exerted by water, we have G. So, we can just leave it as G. On the other side, pressure exerted by water, we don't know the height of the water column, but we know the density 1000 kilogram per meter cube and gravitational acceleration. So, here we can simplify this equation further. I can cancel off the zeros. So, here we have 76 into 136 into G, but G also can be cancelled off. So, this is how we get the equation. 76 into 136 will be equal to H into 1000. So, H will be equal to 76 into 136 over 1000. If we do this calculation, 136 into 76. 6 into 6, 36, 3, 18, 21, 2, 6 and 2, 8. 40, 2, 21, 25, 2 plus 7, 9. So 6, 3, 3, 10. So this has to be 10,336, but we have to divide that by 1000. 10,336 divided by 1000. That will be equal to 10.336 meters. So that will be the height of the water column. So students, here of course I have done the calculation as I told you all, writing the two values as equal. It is equal. So I wrote it together and did the calculation. If you all are not comfortable with this method, you can find the pressure exerted by mercury column. Again use that value to find the height of the water column. Either way is fine. You will get the same answer. So I am sure students, you also have done the calculation correctly and got the same answer. We have done similar calculations before also. Okay. So with that, now I will move on to the next question. Extra question 16. Illustrate using a simple activity that the pressure exerted by liquids increase with increase in depth. So here students, we have done an activity in the lesson. With the lesson, we did an activity in the lab also using a plastic container, a plastic bottle with holes in it in order to identify or demonstrate or illustrate that pressure exerted by liquids increase with increase in depth. So illustrate using a simple activity. So there, I will use the diagram. So here, if we have a plastic bottle like that and we make holes, at almost equal intervals along the same line. So here it is to show that pressure increases with increase in depth. And we fill the bottle with water and we observe how the water exits through the holes. So here there will be water. So the water will exit in this manner. So that is what you will see. So from this, water exits through the holes as shown. So here of course they haven't said to explain the activity. So I'm not going to write the steps, but this is the observation. You can see the water exiting through the holes as shown. So from this, how can you explain that the pressure increases with increase in depth? You can see the water coming out through the hole above. If I mark it as A, B and C. A, the depth is less. Pressure is less. That is why the water is pushed only to a shorter distance. B, depth is more pressure. The water is pushed away from the bottle. And again C, point C, you can see the depth is even more and there the water is pushed further away from the bottle. So that is how we can explain that the pressure increases with increase in depth. So there of course I can write the explanation. Water exits through the holes as shown. So here we can say the depth increases from A to C. The water that exits is pushed further away from A to C. So here we can say, therefore, we can conclude that the pressure increases with increase in depth. When pressure is high, the water is pushed further away from the bottle. So that is how we can illustrate. Illustrate using a simple activity that the pressure exerted by liquids increase with increase in depth. So here of course students, they have asked for a simple activity. So this is a very simple activity. With using that we can show that the pressure exerted by liquids increase with increase in depth. At the same time students, now there is another activity. I will just explain that to you all, where we can have a vessel containing water and also we can have a U-tube like that with water, and this tube is connected through a rubber tube to a funnel with a membrane attached to it. So here we can have water, funnel, that is rubber, membrane, so here you can see a vessel containing water, then there is a funnel with rubber membrane attached to it. It has to be not loose, it has to be a stiff rubber membrane. Then we will have a rubber tube here, tube attached to the other end of the funnel. Then we have a glass of U-tube and colored water. Colored water, why? So that you can say, observe the change in water levels easily. Here we will have water at the same level. So we will have water inside this. Then what we can do is, we can insert this tube with the funnel attached to it into water. And when it goes down, you can see the water levels changing in these two arms. If we label it as X and Y. As you push the funnel down, you can see the water level decreasing in X and increasing in Y. So there are also, the reason is when you push the funnel down, as you go down, the pressure exerted by water will exert a pressure onto the membrane of the funnel. So when the pressure increases, that pressure will push the air through this, and that will in turn push the water column down. So this side x, the water level will decrease, and in y, water level will increase. This is not a very simple activity as the previous one, but you can use this activity also to show that the pressure increases with increase in depth. So here you can say when the funnel is inserted into water and pushed down the water level in x will decrease and y will increase. That is because water in the vessel exerts a pressure onto the membrane. This is exerted to the air inside the funnel and the rubber tube. This pressure pushes the water in arm X down. So, as the pressure in water contained in the vessel increases with the depth. The water level in X decreases as we push the funnel down towards the bottom of the vessel. From this, we can conclude that the pressure exerted by liquids increases with increase in the depth. So that is how we can explain. So students, as I told you all, the first activity that we have done in the lab is a very simple activity, but this is also an activity that you can use to demonstrate or illustrate that the pressure exerted by liquids increases with the increase in depth. So in case you get an observation like this, you will be able to answer the questions. So if I go back and show you what happens there. So this is what we do. We make a setup, a vessel with water. Then you have a rubber membrane attached to the tied to the funnel. Funnel is attached to the rubber tube that again is connected to the glass U-tube. And there is colored water so that you can observe the change easily. And as you push the balloon membrane covered funnel into water, you will see the water level decreasing and increasing in Y. Decreases in X, increases in Y. So, as you go down further, the difference will be greater. We have already discussed a similar one before also. When you tie a balloon and allow the air to flow in, there also you see a difference in water levels. And you know the difference in water level, the height of the water column that is different between X and Y gives rise to the pressure. So here it is the atmospheric pressure plus the difference in height of water columns. So that means if the difference increases, the pressure increases here. So that is how we do this activity. So as I told you all students, since we discussed a similar question before also, I just wanted to introduce this activity as well. So another activity, not a very simple one, but an activity that you can use to show that pressure increases with the increase in depth of any fluid. So with that students, I will move on to the next question. Extra question 17. Write an expression for pressure P exerted by a liquid column of height h. Density of the liquid is rho and the gravitational acceleration is equal to 10 meters per second square. So as you know students, pressure is equal to h rho g. So here also pressure is P, a liquid of height h, density rho and the gravitational acceleration is given as 10. So here we will get the expression as 10h rho. So that is the equation. P equals 10h rho. If the liquid specified above is water and the height of the water column is 50 centimeters, calculate P. So, if the liquid is water, P equals 10h rho. So, that will be equal to 10 into height is 50, but it is in centimeters. So, what do? We divide it by 100. 50 divided by 100 into density, you all know, is 1000. So, here of course, again we can simplify. It will be equal to 5000 Pascal. So, the pressure exerted by the water column will be 5000 Pascal. That is how we get the relationship h into rho into 10. So, 10h rho. So, here in that equation we substitute the height 10 centimeters, but it has to be converted to meters. So, you need to divide it by 100 and density of water is 1000. So, it's equal to 5000 Pascal. With that, I will move on to the next question. Extra question of 18. Some objects float in water, some objects sink in water. The first one, write the Archimedes Principle. What is the Archimedes Principle? When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid that is displaced by the objects. So that is the Archimedes principle. When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So that is the Archimedes principle. When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So I am sure students you would have written this answer correctly. With that, we will move on to the next question. So extra question 19. An object floating fully submerged in a liquid is shown below. So here you can see there is a fluid. It is completely submerged and it is floating. So floating fully submerged in a liquid is shown below. First one, denote the forces acting on the object in the diagram given above. So there we need to denote the forces on the diagram given. So there are two forces acting. The force that is acting downwards, what is it? It is the weight of the object. Usually we use the symbol W, weight of the object. And what is the force acting upwards? It is the upthrust. Upthrust is usually given the symbol or the letter U is used to represent upthrust. Upthrust up and weight downwards. And if it is an instance like this, where the object is fully submerged in a fluid, the upthrust is equal to weight of the object. So we have denoted the forces. The second one, mass of the object is 5 kg. What is the weight of the object? You are familiar with the equation. What is the relationship? Weight is equal to mass into gravitational acceleration. That is equal to 5 kg into 10 meters per second squared. So that is 50 Newton. So the weight of the object is 50 Newton. Mass is 5 kilograms into gravitational acceleration 10. What is the upthrust exerted by the liquid on the object? So I told you all, or you all know, that when an object is fully submerged and is floating, then the upthrust is equal to the weight of the object. So what is the upthrust exerted by the liquid? We can say upthrust equals weight of the object. So that is equal to 50 Newton. Is that clear to you all students? So the object that is completely or fully submerged and is floating, upthrust is equal to weight. So that is equal to 50 Newton. With that, we will move on to the next question. Extra question 20. Weight of an object in air is 50 Newton and the apparent weight when the object floats completely immersed in water is 20 Newton. So there you all can see when it floats completely immersed in water, the apparent weight is 20 Newton. What is the upthrust exerted by water on the object? What is the upthrust exerted by water on the object? What is it? So here you all know upthrust is equal to the weight loss. Weight loss. So this is the equation, students. Upthrust is equal to weight loss. Why? When an object floats in a fluid, the fluid exerts an upthrust and this upthrust causes a weight loss. That is why we see an apparent weight there. So we can calculate the weight loss by subtracting the apparent weight from the real weight or weight of the object in air. So here if we calculate the upthrust, that is equal to weight loss. The weight of object in air is 50 Newton minus the weight of object when it is floating in water, that is apparent weight 20 Newton. So the difference is going to be 30 Newton. So that is the upthrust exerted by water. So here students, you all can see the upthrust is less than the weight of the object. So then if you really put that object into water, what will happen? The object will sink in water. You all know the different situations. We have done an activity also to understand that always when an object is fully immersed in a fluid or water and is floating, the upthrust is equal to weight of the object. If the upthrust is less than the weight or weight is more than the upthrust, the object will sink in water. At the same time, if the upthrust is greater than the weight of the object will be pushed further up so that it will float partially submerged in water or for that matter any fluid, so that the upthrust will be equal to the weight of the object. So that is how the flotation occurs. So in this instance, since the upthrust is less than the weight of the object, if you just put it into water, it will sink. Here of course, because we have attached it to the Newton balance and when we immerse it into water, we get a reading. You all can remember we did that in an activity also. So then the second one. What is the weight of water displaced by object when it floats completely immersed in water? What is the weight of water? It is the weight of water that is displaced by the object is equal to the upthrust. So we have already calculated the upthrust, that is 30 Newton. So here weight of water displaced is equal to upthrust. So that is equal to 30 Newton. So those are the questions here, students. Okay, students. So here also I have discussed a few questions with you all. I am sure you all were also able to do them correctly on your own. And then you listen to my discussion also. So you would have got a very good understanding about the lesson and you know how to answer questions. So with that, students, I will end this chapter here and I will do some more extra questions in the next chapter.